Hi folks, this is Dr. Brown. I was asked to take a look at one of our questions, see if we can figure it out here. And one I was asked to look at was Chapter 2, number 43, which basically says in accelerating from a standing start, so that means initial velocity 0, to a speed of 300 kilometers per hour, and that's our final velocity, the 1900 kilogram super duper sports car exerts an average force. So at 1900 kilograms, that's our mass. Force on the road of 9.4 kN, that's kilonewtons. So we know what a newton is, and kilo means 1,000. The question is, how long does the car take to reach 300 kilometers per hour? So we're given several pieces of information that I have taken the liberty of jotting down. And these are the pieces of information I think we know. We know the initial velocity is 0 kilometers per hour, and that's the same as we need to get to SI units, so that would be 0 meters per second also. We know the final velocity is 300 kilometers per hour, and it's always best to get these in SI units, all the questions in SI units, and that's part of the work here, is just manipulating the units, but we are expert unit conversion artists, so we should know how to do that. So 300 kilometers per hour, kilo means 1,000, so that's 300,000 meters per hour. We convert that into seconds. 1 hour is 3,600 seconds. So it's 300 kilometers per hour equates to 83.3 meters per second. And again, I always strive to get into SI units. Our mass is given at 1900 kilograms, as I said. The force is 9.4 kilonewtons, and a kilo means 1,000, so that's 9,400 newtons. And the SI units for Newton would be kilogram meters per second squared. So the force is 9,400 kilogram meters per second squared. The time is what we've asked to look for. So let's think about this. We're given force, we're given mass, we're given some of the components for acceleration, initial velocity, final velocity, and we're asked to solve for time. So this is a perfect setup for Newton's second law to come into play. Newton's second law says that force equals mass times acceleration. F equals ma. We're given the F, the force, that's 9,400 kilogram meters per second squared, so I plug that in here. The mass we're given also, that's 1,900 kilograms. I put that right here. The acceleration, I don't know. I put A here just as a placeholder for acceleration. But I've got the components, most of the components to solve this, but I am missing one of the parts of acceleration, and that's the time. But I know that my equation for acceleration is shown here. Acceleration is final velocity minus initial velocity divided by time. I'm given the final velocity, it's 83.3 meters per second. The initial velocity is 0 meters per second and divided by time. So again, that's V2 minus V1 divided by t, and t is the part of the acceleration we're hunting for. So when we subtract 0 from 83.3, we end up with 83.3. So the acceleration is equal to 83.3 meters per second divided by t. And time, this is t, time we're hunting for. So if we can figure out what time is, that's the answer to the problem. So with this acceleration mostly known, we plug that in to right here. And that will give us something like this. Let me find a place to, too many things here. I'm going to scoot this little guy up here and then put this little guy right here. Okay, here we go. Now we're off and running. So I continue with my work using this equation, which is Newton's second law, and just start filling in the blanks. This force is 9,400 kilogram meters per second squared, which I got right here. The mass, I know. The acceleration is this right here, which is, I took from here. I calculated the acceleration. I know parts of the acceleration. It's 83.3 meters per second. And I don't know the bottom t. This t is what I'm solving for. Once I solve for t, I've got the problem licked. So this is the basic skeleton of our equation that we have to work out right here. And there are lots of ways to approach it. This isn't an algebra class. If you need algebra tutoring, I'd suggest you get a good algebra book or an algebra tutor. The way I would do this, I'd multiply both sides by t. That would, and that's the time, that's what we're hunting for. My objective is to get t on, or time on one side of the equation and everything else on the other side. So multiply both sides by t, I that takes t out of the denominator on this side and puts t over here. T is time. And then I divide both sides by 9,400 meters per second squared. So I get this. So now this is here, this is here. But after I divide, multiply both sides by t and divide both sides by 9,400 meters per second squared, I get this. And this is just a classic division of fractions. When we have fractions that we divide, we invert and multiply. And I've made the numerator of both fractions red and the denominator blue. So the numerator in my top half fraction is this, is red, and that's the denominator. The numerator in the bottom part of the fraction, and this is the division sign right here, so my bottom fraction, the numerator is red and the denominator is blue. I just did that to try to show you what they were. You invert and multiply. So when we invert and multiply, this comes down, these two terms don't change. This second stays in the denominator, and that second right here, this is right here. This, when we invert and multiply, it stays in the denominator, and this seconds, when it is inverted and multiplied, it flips up and ends up in the numerator. So this is some standard algebraic manipulation. You just take these two fractions, take the second one, invert it, and multiply, and you end up with this. And if we look at this, we can cancel the numerator. If we have a common term in the numerator and the denominator, we can just cancel them out. So in this numerator, I've got kilograms, and in the denominator I've got kilograms, so that cancels out. In the numerator I've got meters, in the denominator I've got meters, that cancels out. In the numerator I've got seconds squared, in the denominator I've got seconds, so one of these seconds will cancel into this to take away the squared term, so my units are going to be seconds. So my units are seconds. And when I go through the math and multiply 1900 times 83.3 times 9400, I'll get 16.8, and that's the answer. So it takes 16.8 seconds, that's the unknown time, if I have an initial velocity of 0 and my final velocity is 83.3 meters per second squared, and my mass is 1900 kilograms. The force the car exerts is 9.4 kilonewtons. So that's the amount of time it takes to achieve this velocity. I hope that helps. If you have questions, please give me a call. Thanks.